In this video, we're going to discuss the Newton-Raphson method for solving systems of nonlinear equations. The Newton-Raphson method is one of the primary methods of choice for solving nonlinear systems of equations. Many engineering software packages, including finite element analysis software, that solve nonlinear systems of equations use the Newton-Raphson method. The derivation of the method for nonlinear systems is very similar to the one-dimensional version discussed previously for root finding. We assume a nonlinear system of equations of the form f1 of x1, x2 up to xn equals 0 down to fn of x1, x2, and xn is equal to 0. So we have n functions and n unknowns. If the components of our unknowns at a particular iteration, which we can say xi, are known as x1i, x2i, up to xni, then the Taylor expansion of the first equation around these components is given by the following. So f1 of our variables x1 at I plus 1, x2 at I plus 1, up to xn at I plus 1 are equal to the value of the function f1 at x1 at I, x2 at I, and xn at I, plus the partial derivative of our function with respect to the first variable, partial f1 by partial x1, evaluated at xi, times x1 I minus 1 minus x1 at I, plus the partial derivative of f1 with respect to x2, evaluated at xi, times x2 at I minus 1 minus x2 at xi, up to the partial derivative of f1 by xn, evaluated at xi, times xn I plus 1 minus xn at I. So applying the Taylor expansion in the same manner for f2 up to fn, we obtain the following system of linear equations, with the unknowns being the components of the vector x at I plus 1. So we have f of xi plus 1 is equal to f of xi plus this matrix of the partial derivatives times this difference x1 I plus 1 minus x1 at I, up to xn at I plus 1 minus xn at I. By setting the left-hand side of the equation to 0, which is the desired value for the functions f1, f2, up to fn, then the system can be written as shown here, where we have the matrix of partial derivatives multiplied by the vector of differences x at I plus 1 minus x at I is equal to negative f of x at I. So if we define KAB as partial fa by partial xb evaluated at xi, then the equation can be written in matrix form as k delta x is equal to minus f, where k is an n by n matrix known as the Jacobian, which is the matrix of our partial derivatives, and in many texts it's also denoted as J. Minus f is a vector of n components, and delta x is an n-dimensional vector with the components given by the differences between our iteration I plus 1 and iteration I for each of our components. If k is invertible, then the system can be solved as shown here. So we can find delta x as negative k inverse f, and then we can calculate x at I plus 1 as equal to x at I plus delta x. So let's see how this works with an example. We want to use the Newton-Raphson method with epsilon s equals 0.0001 to find the solution to the nonlinear system of equations using the same equations that we talked about in example 6.1 in the previous video. So in addition to requiring an initial guess, the Newton-Raphson method also requires us to evaluate the derivatives of the functions. So we write our functions as f of x is equal to 0, so we bring everything onto one side of the equation as shown here. And then we need to take these partial derivatives to form our Jacobian matrix K. So we need to take partial f1 by partial x1, partial f1 by partial x2, partial f2 by partial x1, and partial f2 by partial x2. And we can evaluate all those derivatives and plug them into our matrix K. Now if we assume an initial guess of x1 is 1.5 and x2 is 3.5, then we can calculate the vector f and the matrix K. So f is just the vector of our functions, again written in the form f of x is equal to 0. So we can evaluate those at our initial guesses. So x1 was 1.5 and x2 was 3.5. So this gives, the first component here is minus 2.5, and plugging into our second equation we get 1.625. And then we can plug these into our matrix K as well. Plugging in x1 is 1.5 and x2 is 3.5, we get this version of our matrix K. Then we can calculate the components of the vector delta x by taking the inverse of k multiplied by f and taking the negative of that. So delta x is 0.53603 and negative 0.65612 in this case. We can then get our new estimates for our x1 and our x2 by taking our old estimate and adding this change delta x. So our new estimates are now given as shown here. And it can be noted that if we wanted to apply relaxation, we could do that at this step here by putting in the relaxation factor here. So then we calculate the approximate relative error. So epsilon r is equal to the norm of the difference. So in this case, that's the norm of delta x divided by the norm of our current approximation, which is x1. So after this first iteration, our approximate relative error is 0.2422. And then we can continue the iterations. So using the function nr system that I have prepared in MATLAB, you can see that the method converges after 4 iterations to our expected roots of x1 is equal to 2 and x2 is equal to 3. And these are the values of the vector x, the matrix K, the vector delta x, and the estimates xi at each iteration, as well as the approximate relative error. So you can step through and kind of see how each of these components are calculated and how the estimates are obtained at each iteration until we reach convergence. So you can also notice that the method here converged faster than the fixed point iteration for the same example. The Newton-Raphson method here took 4 iterations, where the fixed point iteration method took 9 iterations in the case that it converged, and did not converge for the other formulation.